are studying energy meter. In our last class, we have studied two important principles. Number one, so if a magnetic field moves with respect to or relative to a conductor, then the conductor also follows or try to follow the motion of the magnet. And another principle that we have studied is that we can create virtually moving magnetic field without actually moving any physical object. Okay. Now, using these two principles, we are going to make a energy meter. How is it? So, the energy meter that we are going to make is made up of an aluminum disc. So, it has an aluminum disc like this, which can rotate around a spindle or an axis, and this above this disc we will have a number of coils. So let me draw them here. Say this is one coil, this is one coil. Let me draw two more coils. Let me connect these two red coils in series so that the fluxes of this and this coil are in opposite direction. Okay. So, these are the two terminals of these two coils, and similarly this green coil will also have two terminals. And now you know that if we have currents in these two sets of coils out of phase with each other, then these three coils together will produce a virtually moving magnetic field below them. Okay. So, it will have some magnetic field like this. It will have the magnetic field in the opposite direction, and the magnetic field of this coil will be out of phase from these two coils. If we do so, then in this region, so this part okay, which is the region below these three coils, will have a virtually moving magnetic field. Okay, and therefore, now this virtually moving magnetic field is moving with respect to this aluminum plate, this aluminum disc. Okay, so if we can create a if we can pass appropriate current through this two sets of coils, then there will be a virtually moving magnetic field with respect to this aluminum disc. And therefore, due to the eddy current motoring phenomena which we have studied previously, this disc will experience a force. So, this disc will experience a force in this direction if the magnetic field is moving in the from left to right or in the other direction. Okay, so the disc will start to rotate. So there is a force on the disc or a torque, so the disc will start to rotate. Okay, now in an energy meter, okay, what we do, so suppose we have a circuit where this is the source, this is the source side. Okay, so these are the two, so live and neutral phase of the source, and here we have some load. Think of this load as a resistive load for ease of understanding. Okay, and this is connected like this. So the source is delivering some current and power to this load, and call this voltage as V. This can be AC as well, this also can be AC. Now we are interested in measuring the energy consumed in this load. Now what is energy? Energy is power times time t, and you can integrate it over time. Okay, so power times dt, you integrate it over time, that will be the energy consumed within a time. And power is nothing but voltage times current, Vi dt, integrate it over some time, that will be the energy consumed in that time. Now, so therefore, to measure energy, we have to take the product of voltage and current, just like we did it for ammeters. Okay, so basically our energy meter need to have two sets of terminals which will take the voltage as input and current as input, and the energy meter is supposed to take the product and integrate the product over time. Okay, so let us, and this is actually going to be our energy meter. We are making the energy meter out of this disc and this electromagnets, and see, we have two coils, red and this green. What we will do, we will say connect this green coil directly across the source. Okay, so therefore this green coil is sensing the voltage Vt. So the green coil, you can call it as the voltage coil or pressure coil, like wattmeter. Okay, this is sensing the voltage. Okay, and now this coil I can use to sense the current through the load. And to sense the current, what I have to do, I have to say open this circuit at some place and connect this coil in series like this. Okay, the diagram seems a bit clumsy, but essentially what I have these two rate coils in series with the load. Okay, so now these rate coils are carrying the same current as the load current. Okay, so this current is IT. Okay. And this green coil is sensing this voltage. Okay, now so for ease of understanding, okay, let us assume that this is perfectly resistive. Okay, so let me copy this. So for our understanding, assume load is resistive. Okay, and if so, and the impedance of these coils, so these are coils means it will have some inductance, of course. So but assume that the impedance of these coils are much lower compared to the impedance of the load. Okay, so the and these coils are current coils, and this green is the pressure coil, voltage coil. Okay, so assume the impedance of the current coil is much lower than load. Okay, so this will imply that this circuit, these coils and this load, they are in series, that is mainly resistive, because this is much dominating than these small inductances. Okay, so this circuit is mainly or mostly resistive. Therefore, the current IT will be in phase with Vt, the supply voltage. Okay, because this is resistive circuit, so current and voltage, they will be in the same phase. But this circuit, this pressure coil circuit, is assume this is inductive. This is definitely inductive. It is mainly a coil. It also has some resistance, of course. It also has some resistance. It is not perfectly a inductor. But assume for ease of understanding that the pressure coil is mostly inductive. Okay, if so, then this current, called this IPC, that means current in the pressure coil, that will be out of phase or lagging Vt by 90 degree. So IPC will lag Vt by 90 degree, and we already have said that IT, which is the load current, is also same as this ICC, the current coil current. Okay, and ICC is same as IT, is in phase with Vt. So what do we see? That this current is in phase with this voltage, and this current is 90 degree out of this current is 90 degree out of phase with from this voltage, and this current is in phase with this. So ICC and IPC are 90 degree out of phase. So these two currents are 90° out of phase, the red and green. Therefore, the flux will also be 90° out of phase, and we know then there will be a virtually moving magnetic field. So a moving magnetic field will be created. Okay. So a moving magnetic field will be created. Okay. So there will be a force acting on this disc, and the disc will rotate. So the disc will rotate. Now, so there is a force on this disc or a torque on this disc. So basically that means the disc will have an angular acceleration because there is a torque. So torque means there will be an angular acceleration. So the disc will keep accelerating. Okay. So as long as there is this force, this moving magnetic field, the disc in principle will keep accelerating. Its speed, its angular speed will increase continuously. But what we will do, essentially what we want to measure the energy consumed. Okay. And so for that what we will do, we will apply a controlling or a braking or a stopping mechanism. A mechanism which will try to stop this rotation of the disc. Okay. So what we will do actually, we will put a magnet, say a U-shaped magnet like this. So this is the north side, north pole, this is the south pole, and this is put over this disc like this. So the side from the side view it will look like this. So this will be the the side view of the disc, and we have the magnet here. North and south. So flux lines are like this. Here also you have the flux lines. Okay. And this magnet is rigidly attached to the frame of the instrument. So this is a fixed non-movable magnet. So this magnet is rigidly attached, so it's not movable. Okay. Not movable. So this is not movable, not moving actually, not. Okay. So this is a fixed stationary magnet, and if the disc is rotating with respect to this magnet, then what will happen? Now once again the eddy current braking mechanism will start. So the disc is now trying to rotate with respect to a magnet, and the magnet so there will be a relative velocity between the magnet and this disc, and we know that a conductor doesn't like to have a relative velocity with respect to a magnet. So there will be a force which will try to stop this disc. Okay. So there will be a braking action. So this magnet is called braking magnet. Okay. So we see there are two magnetic fields, one which is moving, which is created by these AC currents. Another magnetic field is by this permanent magnet. So this is a permanent magnet. Okay. And this magnetic field is trying to rotate the disc. This magnetic field is trying to stop the disc. So basically there will be a kind of fight between these two magnetic fields. One is trying to rotate the disc, another is trying to stop the disc, and there will be some equilibrium established between these two magnetic fields. Okay. So, let us state some facts without rigorous justification now. So, there is a moving magnetic field. The moving magnetic field generates deflecting torque. Td. Okay. So, the moving magnetic field tries to deflect or rotate or turn the disc, okay, and the permanent magnet generates the stopping torque, which we will call the controlling torque. Tc. Okay. So, this is like, once again the situation is like our galvanometer or ammeter, where we have two torques. One is the deflecting torque, which tries to move the pointer, or in this case the disc. Another is this controlling torque, which tries to stop it. We do not have a spring. Instead of having a spring, we have the braking magnet. Now, intuitively, the controlling torque Tc, this will depend on what? So, this will depend on the speed of the disc, okay, because if this disc is rotating faster, that means this disc is intersecting this flux at a faster rate. So, there will be more EMF generated. So, there will be more eddy current induced. So, the torque will also be higher, right. So, the controlling torque will depend on the speed. So, let us take it, I mean, without a proof, let me just tell you that, say that Tc is proportional to the angular velocity of the disc. Theta dot, okay, so is nothing but d dt of theta. Theta is the angular position of the disc, okay. So, this is the angular speed. You can write this as like some constant k1 multiplied by theta dot, okay. So, this is the controlling torque. Now, Td, what does it depend on? Td depends on let's see. So, Td depends on this moving magnetic field. Now, say if I have more current, okay, if this is ICC or same as IT. So, if we have more current here, then definitely this magnetic field will be stronger. So, it will apply more torque, more deflecting torque, okay. So, therefore, this will depend on IT, this current. Similarly, this will also depend on this current, IPC, okay, because if this current is more, we will have more flux. So, the strength of the moving magnetic field will be more, we will have more torque, intuitively, without much rigorous math, okay. So, it depends on this current I and this current. Now, this current is same as this voltage divided by the impedance of this coil. Now, impedance of this coil is a constant. Once we have this instrument manufactured, the impedance is a constant. So this current therefore depends directly on this voltage. So we can say that the deflecting torque will depend on this current and this voltage. Okay, so the deflecting torque depends on I CCT, or which is same as IT, and VT. So this is supply voltage, okay, so which is proportional to IPCT. Okay, so TD depends on these two factors. It also depends on the phase difference between ICC and IPC. Okay, so let me not write the T here, let me just write so this is like the RMS value, which is proportional to the peak or magnitude, whatever. So this is, so TD depends on this two value. If the RMS value is more, of course instantaneous value will also be more. So let me just write it this way. Okay, now okay, so TD also depends on the phase difference between these two currents. How? Okay, so which also means, so the phase difference between this which also depends on, so that is the phase difference between ICC is same as IT, load current. Okay, so this is load current and this is proportional. So this is nothing but the supply voltage divided by the impedance of the pressure coil. So let's write V. So this is equivalent to this and this is equivalent to this. There is a Z or impedance that we have to divide V with, but this depends on this and this depends on this. Okay, so the phase difference between I and V will also decide the value of TD. How? Say here, okay, so we have assumed previously resistive load. Okay, so if we have a resistive load, then we have seen that this current is in same phase with Vt. Let me find some place to write it. Okay, let me write this here. Okay, so for resistive load, this I is in same phase with V and this I, this current is 90 degree out of phase from V. So we have for resistive load ICC and IPC 90 degree out of phase, causing a moving magnetic field. Okay, but for say purely reactive load like inductive or capacitive load, for pure reactive load, what do we have? We will have this current 90 degree out of phase from V, okay, in phase with V, 90 degree out of phase with V, and this current is also 90 degree out of phase with V. This is always 90 degree out of phase with V, but if this is reactive, this will also be 90 degree out of phase with V. So that means these two currents will be in same phase. So for pure reactive load, ICC and IPC will be in phase. Okay, will be in phase or will be 180 degree out of phase. So there will be no, it won't have this 90 degree phase lag. And in a demonstration yesterday, we have seen if these two currents are in same phase, then the magnetic field produced by them, that doesn't move. It only fluctuates. It creates a pulsating magnetic field, but it doesn't move with time. Okay, if these two currents are in same phase. So for pure reactive load, okay, we will have no moving magnetic field. So TD will be 0. Right? So what we observe? We observe therefore that TD also depends on the angle between this current and this voltage. If this current is in same phase with V, then we have a moving magnetic field. Else we will have only a pulsating magnetic field, which will not create any TD. So that's what we have written. TD also depends on the phase difference between the current and the voltage. Okay. So if you think a bit more, then you will possibly realize that TD is like ICC. So this is the magnitude or RMS value, or this is same as load current I, multiplied by voltage. Okay, so this is load current, this is also load voltage or source voltage, which is almost same. Okay, let me just write I and V. And it will also depend on the angle between them. So let me write cos theta. If theta is, so where theta is the, okay, so this theta, let me write not theta, phi, some other symbol, because theta I am using for the motion of the disk. So let me use phi. Phi here stands for the phase difference between V and I. So you see, if V and I are in same phase, if this is 0, we will have maximum deflecting torque. But if these two are out of phase by 90 degree, that means for reactive load, so then ICC and IPC becomes in phase. So this, and also here this will be 90, which means this will be 0. So that's correct. That's what we expect. Okay. So TD is like this. So, and then this is same as the power, load power. Let me just write. So this is load power. Okay. So note that we haven't gone through any rigorous mathematics, any detailed derivation of this fact that TD depends on the power. Okay. But we have tried to motivate this fact by stating, firstly, TD will depend on the strength of the ICC, current coil current, which is same as load current. Secondly, depends on the voltage applied across the pressure coil, which is proportional to the pressure coil current, because if either of these two currents is more, we will have a stronger magnetic field. Thirdly, we have seen with examples that the angle between the load current and the voltage also decides the angle between the ICC and IPC. If ICC and IPC are in same phase, then the magnetic field doesn't move. If they are out of phase, then only the magnetic field moves and a torque is created. So, with this we have tried to physically convey you the fact that TD depends on the power. If time permits, later on we will do a rigorous mathematical derivation, or we will do it in an additional video, but for now we are not doing any rigorous detailed derivation. Okay. So, for now let us try to understand only the physics of the device. Okay. So, TD is proportional to power, and so we can write TD is some constant time power, and we already have seen that TC is proportional to the velocity of the disk. Okay. So, this is what we have already seen. Now, this torque tries to rotate the disk, this tries to stop the disk. So, there will be a equilibrium when these two will be equal. So, at equilibrium, okay. So, equilibrium means say if the TD is more, then then TD minus TC will cause the disk to accelerate. So, theta dot will increase, then TC will also increase, and at some point these two will become equal with each other. And then when TD is equal to TC, then we can write that K2 multiplied by power is same as K1 multiplied by theta dot. So, we can write then power is equal to K1 by K2 theta dot. Now, if we take a integration over time, power integrated over time dt, this side we will have K1 by K2 constant, here we have theta dot dt. So, this will become some theta. Okay, so, if I am integrating this from say time t1 to t2, this will become theta t2 minus theta t1. Okay. So, then the total, this is what the total rotation, total angular rotation of the disk, this is power, and the left side is what? Energy. Energy consumed between time t1 to t2, and this is the total amount of rotation of the disk. Now, what we can do? So, we can connect say gears. Okay. So, let us put some gear arrangement. Okay, I am not good at drawing this gear. Okay. So, assume this is a mechanical gear. So, we may have more gears. And then we can connect this mechanically to a set of rotating dials. Okay. So, these are some rotating dials with digits written on them like 0, 1, 2, 1, 2, 3, etc. So, we have a set of such dials. 0, 1, 2, and this is mechanically coupled. Okay. These are gears. I am not good at this drawing. So, these are mechanical gears, and this is a set of dial. Now, when this disc is rotating, this gear will also cause this thing to rotate, and then this will rotate, this will rotate. Okay. So, we will have some numbers displayed by this set of dials. Okay, and then by reading these numbers we can count how much this disc has rotated. Okay, so we can look at this value of the dial, say at time t equal to t1, and we say see the reading is equal to say 100. Then after say 4 days or after a month we look at these numbers, and then if the reading becomes 300, then that means the total amount of rotation is proportional to 300 minus 100 or proportional to 200. So that will give us the amount of energy consumed in BTH, British Thermal Unit. Okay, some kilowatt hour. Okay, so that's how it works. So that's the working principle of energy meter. Okay, so for this video, this class, this is the main content. You can stop it here, but I will just give you a small thought exercise, a fun exercise if you like. So a small fun exercise. Thought exercise. Okay. What would have been the situation if we had springs connected to the disc? Okay. What will happen if we connect spring to the disc to generate the controlling torque Tc instead of using the braking magnet? Okay. So this is a small question that I would request you to think. Okay. So you may pause the video and think of it, and then I am going to now tell you the answer. Okay. So you think yourself before you see the answer. So what we have this disc, and instead of having the brake magnet, so we are connecting a spring, maybe a spiral spring like this. Okay, just like we had in ammeters, in galvanometers. Then what happens? Okay. Then Tc becomes proportional to k theta, okay, some k1 theta, not proportional to k1 theta dot. It depends on the position of the disc, not on the speed of the disc. That's the main difference. So now what will happen? So at equilibrium we will have Tc equal to Td, which means k1 theta will be equal to k2. This is proportional to the power. Okay. So then what we will have, theta is given by k2 by k1 multiplied by power. Okay. Yeah, one small correction, I missed this factor k1 by k2 here. Okay. Yeah, so then theta is this. So now if you look at the position of the dial of the disc, then you directly have a knowledge of the power being consumed at that point of time. Okay. So then this arrangement will act like a power meter, watt meter, instead of energy meter. So it will behave like a watt meter. That's the answer. Now another small question. What happens if we connect a disc and a braking magnet to the moving coil of an ammeter or galvanometer instead of using the spring. What will happen if we use a controlling torque which is generated by a braking magnet and a an aluminum disc instead of using the spring? Okay. So, think of it. You may share your answer in our forum. You may email us. We will be very happy if you do so. Thank you.